there is the loss function, and the loss function implements the backpropagation and computes the loss for that particular sample that you apply. When I say sample, our sample here, a sequence of 25 signals. Because we grab 25 samples, and that's where we supply it every time for every. And the training here, we're using backpropagation through time. It's an extension of the classical backpropagation for feed-forward neural network that now extended to apply to recurrent neural networks. Another key point that I mentioned last time is that we are viewing the time stepping here analogous to what we viewed before in layers. So every time stepping, it's like as if you're passing through a layer in the traditional feed-forward neural network. So the loss function obviously takes the sequence of input and takes the sequence of targets. And we said in this particular program, the target sequence is just shifted version of the input sequence by one sample. So you shift forward and you say, I want that target. And the purpose of that is that you want the input at time t to ideally give you the output at the next time step. It becomes a one character prediction, right? Every character prediction, okay? So if you look here, I'm going to struggle with moving things here, and I think I can move this one here good, okay? So I can use the mouse. I wasn't able to do this before, and I think this is the largest I can have. And this is the forward pass, meaning that you take the sequence. First step is to converting that integer, which tells you the position of the character in your list, right? And you want to create a vector x with all zeros except one in the location of that input sample, right? So this is an encoding of the character, right? Converts it to a vector, and the dimension of the vector will be the number of distinct characters in your set. Okay, and then once you have the encoding of that character at time t, and you have t here runs from 1 to 25 as we defined it to a sequence of length 25, then you just pass it through the hidden state and then the output, and then this other one here, ps. You convert this output into probabilities by using the softmax. This is how we implement the softmax, right? And then the next step here, once you go past it, then you want to compute the loss function. So for every sequence, you want to get the corresponding loss function. The way you compute the loss function, as is shown here, you take the vector, this is the vector of t, and then you specifically pick up the one entry in the first column and at the position of the target. So you take the corresponding output, which corresponds to the target, and you take the log of that. Obviously, this target is going to be equal to 1, so I don't have to write a 1 here, so we just write minus log of the output. The other outputs, the targets are 0, so we'll imply 0 times log, that's 0. So you only have this loss, which is a scalar, for every sample. And then, of course, you're going to run this over all the samples, 25. That's how you get the loss, which is the cross entropy. Okay? Once you have the loss, now you say, okay, I'm going to go the second part of the backpropagation through time technique, which is going to backpropagate backwards. And you define these initial weights here to be 0, just the same size of the weights. These are for the change of the weights and the parameters. He defines a dummy parameter here to be same size as h of s, which is called dh of s. Backpropagating, you have to backpropagating backward. So you take the same sequence length, which is 25, and you reverse going through t. So you start from the final time, 25, and you go back to the initial time. Of course, instead of 25, you're going to have 24 to 0, right? because we're counting 25 samples and we're starting from 0, right? So what first thing you do, I mentioned last time, and I'm repeating this thing, give you a chance if you have any questions or anything that's, so obviously you take the output here, copy the output in this dy, which is going to be the error signal, and then you focus on the one element of the target, that's the position in this dy. It's all same equal, except now you subtract 1 from it, only when the target is equal to 1. Because all the other ones, the target equals 1, meaning this vector is going to have the desired value be 0 except 1 at this position, right? So that's how you subtract. So this dy becomes the error signal. Once you have the error signal, for the weights associated with the output layer, you just need the error signal for the bias, change in the bias. This dB is just change in the bias. And for the change of this matrix of the output layer, you need the error signal and then the transpose of the hidden units. Okay? For the backpropagating network, you need, he defines here something called DH and DH raw. So DH raw becomes like our tilde in our model, or delta, I'm sorry, and DH becomes what I call lambda. So if I flash what I shown you before, if I can find it here, which is this one here, this is the terminology we used. And in those, if you noticed, last time I discussed about this is the model, but then we readjusted it, and I broke these pieces into two things. I inserted something lambda and whatever, just to make it compatible with this equation. So now I split the backpropagation into two pieces. So lambda here is really corresponding to DH, and delta is corresponding to DH raw. So DH raw equals to DH through this derivative of nonlinearity. Since the nonlinearity is logistic function, this derivative has an explicit expression, which is 1 minus the square of the output. You're going to see this in the equation. So we're going to see this equation, which is for DH. It says the transpose of the matrix in the output layer times the error, and this is the transpose of the other matrix times DH raw, which is this whole thing, I'm sorry, this whole thing here is referred to, this part here is the first DH next. So if you imagine this DH next, you're going to see this one gives you DH, and then this is going to DH raw. So if I flash back and see what we have here, I think I'm here. So if I have the DH raw has the derivative of the nonlinearity, which is because logistic function is going to be 1 minus, I'm sorry, it's hyperbolic tangent, and the derivative is 1 minus h squared. That's just the expression of the derivative of the nonlinearity, okay? Which is explicit because these wonderful nonlinear functions have explicit functions that are useful for computations, okay? That's why people favor them, okay? So they have explicit expression for the derivative that depends on the output signal itself. And this is DH. So that's like what I had, lambda and delta. And before that, this lambda is now equal to the error times the transpose of the weight plus this thing. DH next is defined here to be the transpose times the H raw, exactly like in these equations, 1-to-1 correspondence right now. And so these are the two equations. And then once you compute the H raw, which is the delta, these are the update laws for the associated matrices, the three here. This for the bias, this equal to the delta. And then the other matrices will equal to the delta times the transpose of the driving signal. So this matrix comes from the input to H, therefore the driving signal is X, you have X transpose, and this is H T minus 1 transpose. the math is here, all explicit, okay? So you should feel like they are definitely corresponding. So now, as you noticed last time, he was saying that this is like 112 lines, okay, which is very efficient and well done. Actually, you can reduce this one by one line, okay? Because there's no really need for this DH next. If you look at the mathematical model, I say, oh, no, I'm going to call this one DH raw. So this becomes my DH raw. And then here, I don't need this DH next, which is dummy variable. I'll just take this DH next here and plug it in here. Eliminate this one here. Will be the same thing. And I did this because I know the equations, and I just applied the equations I have. So after all this thing, we succeed in reducing it by one line. Okay? So actually, you can reduce it by this one line. And it's the same thing. So the introduction of DH next is just like confusing. People say, why are you having DH next? It doesn't make any, it's not correspondence with the math. And I think he did it as a dummy variable here. And then at the end, he has DH next equal to this one here. But I can take this one here, up here, and I replace this DH next with DH raw, and I will get the same computation for that step. Okay? So I invite you to test that because I want you to have your hands kind of wet, okay, with the process and not be overwhelmed by this backpropagation because just one network forward and then another network backward. And then once you have the network forward and back, you have the deltas, which called here DH raw, and the DH raw, the delta, will define the updates for all the parameters in the hidden unit, and the error, dy, updates for the parameters in the output layer, okay? Once you have these updates, then you define, as we said last time, this DH, which we defined it earlier as zipping all these parameters together. So DH, the update, I don't see where DH is here. I think it's in the main program. That's where it was. So this is the end of the code, this function. So up to this green, that's the loss function, which is going to produce for us. So you look at the loss function definition. It takes these things, and it's going to produce for us. I'm sorry, no, here. So here, for the D parameter in these guys here, which is this D parameter, just there's one in the code when we zipped all these things into this DH parameter. So DH parameter, which will be really a vector, if you wish, or list that contains all the parameters here. So all of them will be the update, and then you say, for all of these guys, we're going to clip them. The clip function here just says, if any of these parameters exceeds +5 or -5, you're gonna clip it by replacing it by +5, -5. So +5, -5 is the maximum value that any of these parameters can attain. If it's more, you clip it. If any of these parameters is more than 5 +5, you just say I'm going to replace it by 5. So that's a clipping technique, which, because this model, we're going to talk about it later, could have instabilities in some cases, meaning it's not going to decay, it could go unstable. Okay, and we'll discuss it when we talk about gated neural network. This clipping technique prevents it from going wild, going unstable. So this clips to mitigate exploding gradient. Exploding gradient is when those derivatives here, which are coming from the gradient, they are actually equal to the gradient with respect to these parameters, they grow uncontrollably. And this is a phenomenon that's known in the recurrent neural network as the exploding gradients phenomenon. Okay, it doesn't happen all the time, but it could happen for these simple recurrent neural networks. And then this function returns the loss and all the parameters. And in fact, it also returns the hidden unit value at the length, which is the length here is 25 minus 1, so it's going to be 4, which is the last state. Okay, so from this 25, when you run, you have the state as well, corresponding HS. You want to keep the last one because that will be the initial for the next time you run. So it outputs also the last state. So here's the loss function, and if I go back, you see in the loss function, so this is the loss function, but I want to show where, no, this is the sample, sorry. So I think we have to go back to the main.
Slide 24.
So the main, in the main, you see how this parameter, all these parameters are defined to be the zipping of all these different, and the update law. So in the main, you run the loss function by supplying all these inputs, and you get all the returned values here. And then the first step, we said you smooth this loss function, which means for every time you get the loss function, which is over one sample or sequence, you want to smooth it. This is just this step here. I know this is kind of small, so let me see if I could. This smoothing of the loss function, it makes sure that the instantaneous loss function, which corresponds to one sequence of 25, it's not going to make a major change to the value of the loss function. In case that's erroneous, you'll be smoothing it over time. So this thing here is just an expression of a low-pass filter that takes out all the variance changes, okay, and gives you, if you wish, the mean. That's the smoothing concept. And if you notice here, this is a heavy smoothing because the instantaneous loss that corresponds to one sequence that you run, it's going to contribute this little much. The weight is very minimal. So you want to have no impact by a single erroneous loss function. So if one case you have loss function which is large, you don't want it to affect the change of the loss function. If you run this code, even with the smoothing, you notice sometimes it goes up and down. Even with that, there's an impact that things go up and down. If you don't have this smoothing, you're gonna have things like horribly jumping up and down. Okay, because what you're after is really the mean value over a lot of different samples. So this smoothing thing is factored. You notice it's a heavily smoothed function. And you print the smoothing every 100 iterations. So that means you do the smoothing, you run 100 times, and you just print one sample. So what you see out is really after 100 iterations, right? And even when you look at it, as I mentioned, if you ran it, any of you ran it, you'll see that it jumps up and down and then decreases in that fashion. If you change this smoothing factor, you're going to see more vacillation.
But does that still eventually converge to an accurate solution output?
Which one? This one?
Without the smoothing.
Well, it will be, but I mean, it just be a lot of oscillation. There's a huge oscillations up and down, but it will be decreasing on average.
But do we care about that?
You care about which one?
The oscillation.
Well, I mean, because I mean, you don't want to be misguided while you're watching it, right? You don't want to have things where you don't know where you're at. So the smoothing just gives you where the effective mean is going. So you want to see the effective mean. You don't want to be distracted by the instantaneous fluctuations.
Okay.
We want to see exactly where the core is going. And he's smoothing it here after 100 iterations. Okay, that's a choice that he made. So I'm sure he optimized this one in here and says, for this one here, I see good results. Okay? So that's the thing. So let's see what else we can see here. So that's the loss function. Any questions on the loss function? Because it's important. You're going to be asked in the mini project to monkey and play with this one here a little bit. So you have to study it. Okay? And the other thing, important function, is the sample, which we talked about last time. And I'm repeating again just to give us an opportunity to ask any questions or any reflections. So the sampling, if you would, it's like the testing. It's a testing process. Okay, sometimes people use the sampling in stochastic systems to represent a testing of the performance. So what happens in the sampling? You supply H and a seed, which is just an integer. The seed Ix is integer, which is one position, which corresponds to a character in your sequence of unique characters. For whatever text, you define the vocabulary, which is the sequence of unique characters, right? And then every character is going to have a position in your list, and this seed index just says where that position is. And of course, when you get that position, the first step is you encode it. You convert that position here into a vector of the same dimension of the vocabulary size with all zeros except one in that position. That's how you encode that character, right? So that's just the encoding. And then here, he's adding something indices, which is going to be a sequence. So he's going to have this one to sum to it, append to a list. And the process here for this sampling, what do? You already have the weights frozen in this case. So for these weights, you're going to run the system. This is an inference. The word inference is used to mean that you are doing testing or performance. You're not training, meaning that the weights are all frozen. You just have data come in and you see what the performance is. So this inference you have, this n says how long. So n you supply it. In the program you selected 200, if you look at it, which means I want to generate a sequence of length 200 in this particular case. That's a choice, depending on the size of the text you have and how long you want to follow the performance. But now we have the initial vector, and you supply this initial vector here to forward. So this is the forward path, all the way to P, which gives you the softmax. And then this is the step. So once you have the softmax, which is a vector P, tells you the probability of each position. Remember, each position represents a character, right? And then what's the probability of each position? Each probability is between 0 and 1 because of the softmax, right? And then you have this probability, and then here's what they use here. You use something called in NumPy, which is called random choice. This random choice, it gives you a range, and it's going to select one integer from these guys. You have the integers, which is the characters positions, right? 24 or whatever the number of characters you have in your text. And then it says do that with this probability. So you use the output as the probabilities, okay? And this random choice, you don't say I'm going to pick the maximum. So that's what he's doing here. So typically you just want to pick the maximum and go, right? So you pick the maximum and say that's the output. But here they inserted some wrinkle and they're saying no. I'm just going to have these guys as probabilities. I'm going to have this random choice, which is going to pick the vocabulary position from this range, which is the index, with these probabilities. So adding some stochastic nature. So typically it may pick the max, But if you have things very close, a lot of probabilities are very close, it may pick something else, the next max. So I'm assuming that this random choice, if the output here has one which is close to 1 and all the other ones close to 0, most definitely it will pick that max. That's clear cut. But let's assume that the outputs have many probabilities that are very similar, very close, within some range. Then I personally don't know exactly what this random choice does, but it's going to use some probabilistic thing to select one of these guys with the probabilities. Okay, and the bottom line, it's going to produce an index. Once you have the index, you have the encoding for the index to match a character. And the index here that you pick, you're just going to store it. Now that index corresponds to a character, right? So what is that point? So the way they do the sampling, you give them an initial character. You run through the network, the trained network, and it's going to give some output. You use these outputs, all of them, as probabilities to help you have random choice select the most likely character. Okay, typically will be the one with the largest probability, if that largest probability is dominant. But you have all the outputs maybe have more than one likely, right? The next character could be N, X, Z, whatever, depending on the word. Here, just like it's a toss. So randomly they give it another one. Once you have that input, gives you one output, you take that particular output that you randomly selected and you feed it into the next time step and pass it through the network. That's what this thing here, right? Produces one, you select the next highly likely, probabilistically. So that's why they refer to it not testing, it's a sampling, because there's stochastic process in this one. So in this case, it's character based. So you're going to have sentences, and if there's similarity, you have two words that have the next character the same, then it's going to pick one or the other. Okay? And there's some stochastic nature, so also it's not tied in, so you produce the same result as in the training data. You're not really, so you want to have little flexibility to change to another similar word. Okay? So that's what, and then you return the sequence, which is going to be 200 characters or 200 positions or integers, which correspond to positions, and then you go and convert it back into characters and you print it out in the main program. Yes?
So the guy that wrote this, I guess that he must have saw that adding this stochastic nature, this random choice, was beneficial, or
yeah,
because I kind of don't understand why you just don't go with the max from the software.
Oh, because I guess I guess then you're likely to kind of reproduce. Then when the loss function goes down very small, then what you're going to end up with, if you have a text, you're going to reproduce the same text, right? So you have a training text, and if the loss function goes very low, very small, right? Then the end of the process, you'll replicate the same text. So there's nothing gained, right? His purpose is to have some little randomness and to not generate the same training text, but generate things that have the same style of that text. So that's why when you look at the writing of Shakespeare or Nietzsche, okay, they're trying to generate a text that have the flavor of that writer, but not exactly the same training text. So that's the key point. I mean, these people, they're a group of people who are pursuing that line, and they're interested in that process, and they're trying to find applications, and this person pursued it further and applied more advanced kind of recurrent neural network techniques, which uses, other libraries such as the PyTorch, or other libraries more advanced. So he wrote this program for the simple model, but for more sophisticated stuff, he used other models. What is the purpose? They are seeking to have a network that from training, it gains the flavor of a writer and could potentially write another novel, okay, with the same style of that writer, Steve King, whatever, write a new book of Steve King. That's at least the thing that they're pursuing, okay? So let me continue with that. So here's what they say he used that program for. So here it is, Welcome Shakespeare. So he took William Shakespeare, several textbooks of William Shakespeare, and he trained the network, and he's showing us here a sample of his experience of the training using the same model. And he's saying, like, initially when you train it, this is character level. So it gives you a text like that, which makes no sense. Then you keep training, and it starts converging to something, and then here at the end, he has something that meaningful, okay, and he shows, he shows like what the training is and what the outer final product is. Obviously, I'm not advocating this method in any way. I'm just sharing with you this particular experience that people have done 2 years ago. And I bet you some people are pursuing this line of activities, and it could lead to some very useful things. Hopefully will improve models. So the concept itself is not far-fetched if you have the capability. So the idea is to have a smart system that could do that. Mimic, can learn from a human being, okay, a writer in this case, and replicate the thing. And he's showing you some example of success, okay? So this is what the network after training simplified. He also was courageous enough to apply it to algebraic geometry, some books with proofs and theorems, and teach it all these different characters, and had the LaTeX source code, and he claims that he was able to produce things that trying to mimic a mathematical textbook. And so, they're using it like exploration, fun, this is what the graduate student was doing. This was not part of his thesis work. I know because his work was different and related to natural language, but this is something that he did and provided for the community. So it shows one example they're making a joke of is that something that goes in graph geometry and then has proof omitted. That's what the network produced, or something like as a joke. And sometimes it makes very silly mistakes. Another example of teaching it examples of C codes, and wanted to see if it can generate a C code, and it generates to a certain extent parts of a C code and fails in some miserably in some really basic human things. So and you can read about and another thing that that they try to do in this case, which it doesn't make any they were hoping that they could actually by the structure of the network, once it's learned, they want to have things that you can interpret what each block of the network does. So one thing, the reason this interpretation is very big in recurrent neural network, because a lot of people, particularly in insurance companies, that they don't want to have what they refer to as a box. You just have something and gives you the result, right? So they want to have some logic behind things. So that's why some people pursuing this interpretation in every block of the cell. To me, that doesn't make any sense, but at least that tells you the exercise that people do in it in terms of excitement. So they're trying to identify in the neural network, what the logic is of what it's doing after training. But that's too simplistic because the whole structure of a neural network is really not to, the structure itself doesn't have any logic. It's perhaps maybe some parts of the sequence of the mapping that has the logic. Another thing, which I'm going to start, and I'm going to revisit this part in this handout, is people explored this image captioning application. The image captioning concept says if we have a convolutional neural network that does good classification of images, so I have an image, and this neural network can tell me that this is a person, okay? And when you look at the image, you say, well, the image has other things. You need some captioning which describes the contents of a certain image. So some of the connections with convolutional neural network is that some people have connected a recurrent neural network to a trained or almost trained convolutional neural network, and they continue training with this recurrent neural network, okay? Trying to train it so the recurrent neural will generate a text that will be the caption of what's in the picture. So imagine you have this image, you already have this convolutional network that maybe sends this image to a class, let's say class A or class 1, and then you want to use this class to drive recurrent neural network with a trained sequence describes what's in the image. So it says perhaps you have signal that encodes the starting of the sequence, then you have a straw. So when you start the sequence with this image, it's going to give you a straw, and then you use the straw here, it tells you hat, and then you use the hat, tells you end. So straw hat is associated with this image. This is just an example. So a recurrent neural network could actually generate sequences, and one application is this image captioning. Okay, so this is just the structure of how sandwiching or cascading or sequential setting of a convolutional neural network followed by recurrent neural network. So there are many people in the community who actually started this one, I would say, in the last 2 years or so. So this just walks through how that process is doing. And it shows you using a basic recurrent neural network. So if you have something already trained like this, you want to have a signal from this train that links with a recurrent neural network. So what they've done is they take an optimized convolutional network that won some of these ImageNet competitions, something that people say, okay, here's the structure, and this structure has weights. These weights are stored, you could read them in, you have this structure that's been trained about 1,000 classes of images successfully, and it achieves for you something above 95%, for example, okay? So the procedure that they've done, this is just an example procedure. They say, what if we take the last 2 layers of this one here, we freeze this whole thing here as it was, and you want to take this last 2 layers because this one was giving you whatever 1,000 classes of different objects, but now I want to link this output here to a recurrent neural network and train only the recurrent neural network. So view this whole thing as a mapping, pre-processing step that's frozen. This one takes an image, gives you some representation of it for that image. That's different from other images. And then you take this representation, either you remove this one or don't remove them, that's optional. And then you take this data and you want to link it with a feed-forward recurrent neural network. So let's see. So the way they link it is that they take the original structure of recurrent neural network, right? That's the recurrent structure, the hidden unit, and they insert another block here, which is WIHB. So he shows another term. So there's another weight. So if this one is 4096 vector, you need a weight that maps this vector into some vector of dimension of the hidden units, just a transformation. Now, all these weights now obviously will be updated with the backpropagation through time. So the change that they have is that they have a way of having this output inserted here. Okay, very basic steps. Then they say, okay, once you have that model, well, then we just have something that represents a vector that starts the process, one unique code, which view it as a character, okay? And that once you have this character, it says, I'm starting the process anew, right? And then you want to train it, you get this output, okay? And then if you sample, you select it by whatever technique you say, you supply this straw, and then you say whatever the number of sequences. So in this case, showing us an example of 3 sequences. Because I want to connect it only to 2 words, straw hat, right? So start, straw hat, and that will be the end, okay? So that's how you structure it. I'm walking through a specific example that people develop that is an example. There are a lot of different ways you could modify this one. So they also have some references, I guess, in 2014 where courageous people were dealing with huge data. An example would be the Microsoft COCO data. I think it says currently 120K, I mean currently maybe a year ago, 120K images, and it has 5 sentences each. So now they increase 5 sentences for the caption. So they take an example they're showing you here is an image, and they train the network, and then it's going to train it so it generates this particular 5 sentences. And you train it, and of course Microsoft had a lot of resources and clouds and what have you, and they have a lot of engineers, and they just crank these things day and night, and they, after a long training, they can get these things with the COCO data set. So here's an example of a paper by several people in 2014 that applied it to this data set. And they were able to, once you give it this image after training, you're going to have the corresponding text like that. And they actually went wild with this. These are other example images. And they show you obviously successful things, but here's one I think it's not successful. A young boy is holding a baseball bat. So things of that sort. So obviously they show you all the success things, but there are things where things fail. But imagine if you have all the resources and the training, and you have a huge network, and you just do a night, you should be able to do that, and people have demonstrated this one. Okay. So, and there are other architectures. So now, the RNN, the basic simple RNN, it has these problems sometimes when the gradient go wild and they are not constrained, and that's why the clipping was a quick, if you wish, unclean solution to that process, but that doesn't eliminate the instabilities that they've seen. So obviously there are other models. So here's the structure. You have an image. This is a feature, convolutional feature extraction. This thing is transforming this whole image into representations, a vector representation that distinctly differentiates between realistic classes of images, gives you the right classes. Then you could use this one in some recurrent neural network. This code is LSDM. We're going to discuss it in a few minutes, which is a modification of RNN. And the process here is to generate a text. And people still to this day, they're pursuing this process. And it's just not just Microsoft. I mean, all these big players, they're all doing it. And this is also related to tagging. If YouTube or Facebook gets an image, they want to write a paragraph about that image. In fact, they also image tagging. When you upload your own image, it tells you, can find out who your friends are, and can tell you who is in that image. So that's at least pursued by these companies at a large scale. Okay. So, okay, let me just pursue this one since it's here, because before I can go to the notes, because I think it has it, and it's very cleanly done here. So the so-called simple RNN, okay, known these software companies as Vanilla RNN. So if you ever go to Google, you have to say Vanilla RNN. You can't say simple RNN. Okay, they would not hire you unless you say Vanilla RNN. It's almost like a written code, because all these young people are having fun and doing all these things, and they want to call it vanilla because it wasn't producing the good results that they wanted. So there's a relation between the so-called, this H stands for hidden units, and you have nonlinearity. Sometimes, mostly, it's the hyperbolic tangent for the simple RNN. And you have augmented weight, which is weight for these two signals. And in this case, they're calling these the previous signals. It's not showing the input, so there's also an input here which is not shown. But in this case, it shows you an H at, let's say, layer L. So use time as an index here, subscript, which is the book that we have right now, uses time as soup, just for notation. So there's no escaping from all these different books using different notation. So typically when I advise you, if you read a reference or a book or a paper, first thing, establish what the notation is, okay? Because so that online textbook use T, which is the time, and it has a subscript. And I think it makes more sense to use T as a subscript, as a tradition, and use, in this case, if you want to create a layer within the recurrent neural network. So you have this one, a layer, as a function of prior layers. So this is the same layer with time delayed, and it also has it as the previous layer with the same time. And if you take this previous layer as an input, so I'm having a layer and then you have an X here. So this is another fancy way of just rewriting the model. Okay, it's the same simple RNN model. Okay, just now if you view it, instead of having input to hidden units, you're saying, oh no, I'm going to have this whole recurrent neural as a layer. So my input could be an output of a previous layer. So here's my previous layer is L minus 1. And this notation, I think, it makes more sense than the notation in the online textbook. But people have whatever their preference. Obviously, you have a lot of people coming from different communities, different trainings, different flavored characters, and you should make sure that you understand what the terminology is and what you're reading before you pursue it further. So they're saying the difference between the simple RNN and the so-called LSTM, and LSTM stands for long short-term memory, is that in this model you have signals I, F, and O referred to as gates. And these gate signals use nonlinearity, which is sigmoidal nonlinearity. The sigmoidal nonlinearity runs between 0 and 1. It's a sigmoidal function, which we should all memorize by now. Okay? And the hyperbolic tangent is similar to the sigmoidal, except runs between -1 and +1. Okay? And he's writing all these expressions in a very efficient way, saying these guys, these are nonlinearities, they're going to be applied to an augmented matrix, WL, which instead of this one L here, or that has this dimension, this matrix is going to be four times the rows, and of course the same number of the columns. So the LSTM adds 3 gating signals, which are in a way replica, copies of the simple RNN. So it's like you have the core simple RNN, and you create 3 replicas of the RNN, and you say these replicas, I want them to serve as gate. And the extreme, these gates going to be either 0 and 1. Okay? When it's 0, that means you're shutting off that gate. When it's 1, you let it open. Okay? And I'm having 4 times the size of the original dimensions, right? H. So H here of dimension n became these things here of dimension 4n. And then the so-called memory stuff is adding this term. And this term is referred to as the memory cell. And what it does, it just creates an intermediate variable, which is going to be a vector called the cell vector CET at time t and layer L. It depends on the previous vector time and time, this one here. And this circle with a dot is the mathematical point-wise multiplication between a vector and a vector. So you have 2 vectors and you point-wise corresponding element multiplication. This is what it is, and mathematically is referred to as the Hadamard multiplication. It enables you to multiply 2 vectors, just point-wise. If you don't see the vectors, if you see matrices, then this is the regular matrix vector multiplication. Okay? And in Python, this one represented by just a star. Point-wise multiplication. Right? So it takes this cell and it has the previous cell value with this one here, point-wise. And then you have this I, which is the gate at the input, multiplies this G, which is the simple RNN. And this point multiplication is that, look at this I. If any component of I equal to 0, that means you're shutting off that contribution. If any one of these i's equal to 1 in the extreme, that means you're passing on that thing. Of course, this logistic function expression is going to be between 0 and 1. So you're viewing this I and F and O as 3 gating signals. Imagine the extreme in the logic thing, these values of I, F, and O is just 0 or 1, meaning pass or no pass. It's a gate. Of course, you represent it as a smooth function logistic, which could be between 0 and 1 smoothly. So you extended this original model to this model by having these three signals you generate as gates, and if all the gates equal to 0, then this H will be 0. Okay? Right? If all the gates equals 1, then if the F equal to 0, I equals 1, right? And O equals 1, then the expression here become exactly equal to this simple RNN. So what is the point? The point is that this model, this cell, adds flexibility and capabilities to the neural network and makes it part of a family of gated neural networks, which intuitively it helps control the blowing up of those gradients. So when the gates equal to 0, then basically the gradients cannot grow, right? Gradient also becomes. Okay, so the idea of having the concept of exploding gradients is that subsequent gradients will depend on prior gradients. So if you look at the equations of the backpropagation, you have a lot of nested multiplications. And if in this nested sequence of multiplications, some of these things grow above 1, then over time, intuitively speaking, could grow. Or it could shut down. If every stage in a sequence of multiplication is below 1, then eventually you're going to kill the contribution of the gradient. That is the motivation. So you see here, when you talk about the LSDM further, people went so wild in creating a lot of graphs. To some people, some communities, these graphs more meaningful than the equation. To other people in different communities are the opposite. So some people find it easier to see the graphs than the equation, and vice versa. So let's see what this one says, this one here, which I think was developed by the original people who introduced LSTM, and in '89. It's an old kind of model that was introduced then. And I think I've seen basically this one in their work. And the idea is that you have this one here will be like for the simple RNN, and this and this and this are the gates, and the gate multiplies the output of this one here. This is a multiplication. This is a pointwise multiplication. This is the recurrent signal multiplies with this other gate, and this pi here is another multiplication. So you have three gating signals controlled by these I. This is I, this is F, and this is O signal. And so if you take those things away, if you don't have these gating signals, you just have the original simple RNN. You have the nonlinearity, the hidden units, and it just passes out. But you insert three gating multiplication pointwise to control the flow of the signal. That's the basic idea. And the motivation of that idea is they're saying, how can we solve this problem of exploding gradient and diminishing or vanishing gradient? These are the two terminologies people have used over the years in trying to overcome this instability. And clearly, this structure has succeeded in overcoming that issue. And people have seen a lot of positive results with this extended model. LSDM became very popular. In fact, you see it currently. This year, you see applications of a lot of different models using LSDM. So LSDM became the true working horse of recurrent neural networks. And if you look at the Google Translate model that was generated, I think, a year ago, which actually succeeded in demonstrating efficient, good translation among different languages, English, Chinese, French, different multiplicity of languages. Actually, when you look at the details of that model, you see a family of LSTM models incorporated in it successfully. Okay? So I described only one of these structures, but people favor different things, and there's some, historically, this is the cleanest one that's used now. Historically, people try to have other links, so they have graphs and they have other connections, more complicated than others, trying to solve some pieces. But I think what transpired right now, that the basic LSTM often refers to this one here. I'm going to continue with this until I see something where I can introduce this other stuff. So, so this one, the Hochreiter et al. 97 or 98 paper is the one that actually introduced this original model of LSTM. Was neglected for some time until it started showing tremendous results, mostly in competitions. So, you know, people, when they demonstrate things of something like ImageNet or some speech recognition or translation, when they see the outcome and the results, people pay attention and say, okay, there's value in this. So only like I would say in 2014, 2016, that you see tremendous proved results using these models. So as I mentioned to you, here's another graphical, maybe easy way of appreciating the model. And you could see this is the mathematical model, this is the cell, and this is the hidden units, and it shows you how to insert these I, F, and O, the gating signals, and the gating signals have nonlinearity sigmoidal, and only the last signal has a hyperbolic tangent. Okay? and you see immediately that in terms of computation, you're going to have 4 times the original model. And 4 times in terms of the vector, and of course, the number of parameters also is going to exceed what it used to be. These are the signals, and this G is the basic simple RNN, and that's how you combine them with the cell. So and he's mentioning like variants and friends, and people have worked so hard because, so notice like that was in 79, and this one is 2015. So in 2015, people have looked at the obvious thing is that this model is 4 times whatever it was, meaning the dimension of the parameters will be in order of 4 times, right? So if you deal with things that are in the 100 or 1,000 dimensions, you imagine how many parameters, and the training could take weeks, even on GPUs and the clouds. So has been a trend, and this trend is showing up like in 2015, is can we have reduced this size, okay? So if in the Google Translate reference that I mentioned, they use not just one LSTM network, they have at least 8 of those cascaded in layers. So imagine if every one of them is like 1,000 dimension, the hidden units. Imagine how the weights are and the computation. They take weeks to train, okay? So the trends has taken the LSTM and tried variants of this LSTM. And in this paper, I think they explored empirical explorations of recurrent neural network architectures. These people, I believe they were at Google, and they were did extensive trials and error trying to find what various versions. Okay? So that's one. Also, there's another group that created what's referred to as gated recurrent unit RNN. Okay? So that if I go back to the LSTM, and that's where the complexity is, the gated recurrent neural network says we don't need 3 gates. Perhaps we can do away with only 2 gates, meaning that one of these equations and the associated parameters could be eliminated. Okay? And they were shown actually in some results that yes, they could do that. They got rid of one of the gates, and that tremendously eliminated a lot of parameters, speeds up the process. And their message is that we can get similar performance to the original model. And they demoed that using traditional data sets. For example, you begin with the MNest, you move to other data more complex than that, and you show that performance of the original LSTM, which replicates 4 times, is having this other reduced network that only replicates 3 times, and you get the same performance in the testing data, and you say, why do I need to use that larger network? So there's now, since again 2014, 2015, there's another group of people who are advocating and pushing this so-called GRU RNNs. I can quickly highlight some aspect of the GRU. The aspect saying, when I come to this equation, why do I need to use I and F independent gates? They said, I can use one of those guys, I or F, and the other one will be 1 minus that. So for example, you have a gate I, and F, for example, becomes 1 minus I. What happens there? Then if this, in the extreme, when I equals 1, the other one will be 0, and vice versa. In other words, we don't have to gate both of them. We can just have one gate and passes one or the other. Why pass one or the other? If passing this simple RNN contributes instability to the gradient, we're going to shut it off and only pass the previous value. In other words, we freeze this C. So this becomes 1 and this becomes 0. And this equation now, just whatever C you had, just keep passing it. Okay, so if it starts going unstable, so no, it's going to go unstable. Just freeze this C, and therefore H will be frozen. And therefore, I'm not going to grow that gradient anymore because there's no change, there's no gradient. I'm just stopping, right? So they said this one gate, perhaps, which save us one replica of simple RNN generated. So that's one feature of it. So if you look at this GRU, even though they rename these gates, okay, in my opinion, the only thing is just take this one and simplify it. You can use the same names as the original gates and just show where the difference is. The difference is here. So you have something Z on one side, and this is 1 minus Z. So you don't need to rename this as Z. Okay, you could just have it as I, O, and F. Of course, if you look at carefully at the equation, you discover that they change slightly other things. However, this one took off. It has 2014, the starting date, and established another community or another group that's pushing this one. And you can, so you could notice that this is the 2 gates with sigmoidal functions, one basic network, and then they insert this one here. So even though you have this one here, you have this is what shared gate, if you wish, and then this is another gate. So you have 2 gates, 2 independent gates, R and Z, and you compute those. So we had some work where we can show actually you take this one, you just reduce it to this one. They're related in that one direction, okay? In our work, we do that. We don't say this is totally different from that one, okay? And I think there's, to be fair, I think there's some minor differences, okay? But you can account for them by making sure that how they relate, and that's important, okay? So I don't want to be, I don't want to give the impression that this is simply taking this and reducing it that. But there are other aspects to it, but I think you can make the connection that they both of them come from the same source, which helps better understand how all these things are related. Okay? So that's the GRU. In fact, even though it's not listed and somehow in these things, there's another modification, I believe in 2016, that says, hey, we don't need 2 gates. I can do similar things with 1 gate. Okay? So when that person says, why do we, for example, carry this one here? We don't need this other gate. We can just turn off this other gate totally. We don't gate this one. If we gate these 2, that's sufficient. Because this one eventually is going to come here, and it's going to come here, it's going to be gated. So why need to gate this one, and then you pass and you gate it again? So don't gate here. Throw away this other equation R, and they end up with 1 gate, okay, and you get this one. Now, obviously, you can reduce things to whatever, back to the simple RNN, okay? But every time you reduce something, you have to establish some evidence that your reduction did not lose performance. That's the guidance. So if you reduce it and you say the performance on these, using these metrics, using this established public data set that everybody has access to, okay? My performance, and I compare those things, I'm within the range, I'm better, I'm equal, I'm slightly worse. You establish that, you advance it, and you share it with the community, right? So it makes sense. But of course, if you reduce it, and your reduction gives you lousy performance, nobody's going to pay attention. That's just a waste of time. We're not going for the reduction. We can go with the reduction as long as we maintain the performance that we get. So when you want to do a translation among languages, and with the LSTM, Google, for example, between 2 languages achieves maybe 92%. Okay? Then this becomes the standard. If you want to have a product and you want to compete, do not get things less than 92. Right? So so if you reduce it, I'll be happy to hear that. You show me what you've done, but do not lose the quality of performance. Or you do not lose it by much. Maybe if Google has 92 and I can get something reduced with 91.7 and I can have it maybe a lot less. Maybe somebody's willing to work with it. Say, I don't want to spend this thing with Google, and I can do that. So that's the guidance. So the performance on the testing data is critical in allowing you how much you can reduce, but lots of people are interested in this reduction. There's a great interest. So if you are thinking, and we all are thinking towards mobile, you don't want to use the cloud every time, right? And if also you're interested in security, because you say, oh, I have the mobile, I can use the cloud, does the work for me, then the cloud's going to send me the parameters on my mobile, and I have inference on mobile only. If I need to train, I go to the cloud. And that's what Google is saying, right? But then what if you worry about security, right? What if you really want things on the mobile itself? You either have something with some super computational platform on the mobile itself, which we don't have yet, or you can look towards reduction. Okay? Those are the 2 avenues for this. So here's the summary. RNN has flexibility in architecture. The simple RNN worked very well. So obviously they work, but not very well. Don't give the same performance. They sometimes have instability. Common use, LSDM, GRU. Their additive interactants improves gradient flow. Backward flow of gradients in RNN can explode or vanish. That's why you need the LSTM as an example, or the GRU. And I told you there's another one, but people have not paying attention to the other one much because maybe it has not been tested as much, the one with a single gating. And simpler architectures are a hot topic of current research. So this is not my statement, what I just said. It's from these people from last year. Okay, better, simpler architectures are a hot topic of current research. Everybody's after that. Better understanding, both theoretical and empirical, is needed. Because people sometimes they have a model, it works very well, and they translate very well, but they lack the understanding. They cannot extend it. Okay, so that's okay. Actually, I came to the end of things, so the time, right? So I'm going to have my own take on this one, my own slide, which is going to be uploaded. The updated one will be uploaded. It's the same. We have it already. And I invite you to read this one and read the other slides and dig deep in this and ask questions, okay? I'm going to stop at this point and wish you the best, okay?